Let's start. Hello. Yeah, thank you for that. Yeah. So, let's start. Hello, everyone. I hope you all are doing great. And
Yeah,
it's nice to see you again. Uh, so let me start by taking a few questions first. There are a couple of questions in the chat. Uh, yeah, so one question is regarding generators with an I in front. Yeah, you can imagine that's kind of a convention. Mm, and yeah, in fact, we have already seen a generator with an eye in front when we discussed. We will also discuss today again when we discuss this um, the U1 symmetry of the complex scalar field. So that has an eye in front. Mm, then the next thing is what is space and time intrinsically? Okay, so space and time are the dimensions. So as you know, we have three space dimensions and one time dimensions. Uh, so that's what it means. I don't know what to explain more here. Okay, I hope that's clear. Okay, I can add one more thing that because of relativity, we treat the spatial and the time dimensions as the as like on the same footing. So in that sense, though prior to relativity, you are not used to treat time as a dimension. Special relativity tells us that space and time are the same thing, so we treat time as a dimension too. The only difference is when we are inside the light cone, which is our universe, which is like nature, then you are allowed to move left and right in space, but you can't do that in time. So you can only move forward in time. So time is unidirectional in the part of the light cone that describes nature. Okay. And we'll see today itself a very interesting consequence that comes out of this when we discuss propagators. Okay, so I think let's start. So yesterday we quantized our theory, and we ended up building single particle states. So let me briefly recap. So we saw that if you computed the commutator of the Hamiltonian with this quantity AK dagger, then what you got was you got the energy of the state as just omega k, and the same is for if you act it with um, the BK daggers, and if you compute the commutator with AK, then you got minus omega k AK. Okay, so this means that the state AK uh, dagger actually creates a particle in momentum space. So this means that this is a particle in momentum space or an excitation. So, sorry, a particle or an excitation in momentum space with energy omega k, where recall this omega k was written like this as k square plus m square, right? So that's what it means. And similarly, this state also has the same energy. Okay. Now let's understand what are the differences between the two kinds of oscillators. So for that, we need to understand the symmetries. So to study the difference between the A and B oscillators, let us look at symmetries, which we already had seen. So that symmetry was U1. So if you take phi to e to the power I alpha phi and phi star, which is the conjugate, means it will go to e to the power minus I alpha phi star. And this E I alpha was rank 1 unitary objects, matrices. So that's why this is a continuous global symmetry, as we had discussed before in the classical field theory setting. So now let's look at what this does. So recall that we had defined its Noether charge for this symmetry. So if you remember, under this symmetry, the Lagrangian, the variation of the Lagrangian itself was 0. So which
Invariant.
implied, sorry?
Invariant, yes.
Yes, yes,
Lagrangian.
yes, yes. So that means that the action is obviously invariant. And the Noether charge that we had defined was defined like this. Okay. So that's the zeroth component of the current, as you know, of the Noether current, integrated over 3 volume, whole volume. Okay. And so if we promote that to operators now, as we have been doing, so this just means uh, that this is what we call the canonical momenta times phi minus the dagger, the Hermitian conjugates. Okay. So now if you, again, this is an exercise, but a very straightforward exercise. We now know how to work with the integral signs, Fourier decomposition, working with commutators inside an integral. So again, this is a very straightforward but a bit tedious exercise to show that indeed when normal ordered gives you this quantity. Okay. AK dagger AK minus B dagger B dagger B. Okay. Okay. And these are vectors. So let me again remind you, this was a nice question asked last time. So that's the expression. And here I am using a notation for the lectures that I'm writing on the iPad. In the typed lecture notes, it's clear. So when I'm writing like this, it means that I am denoting a vector. Okay, so I'm not giving the arrow explicitly. So these are all vectors. Okay, but in the typed notes, you will find the arrow. So that's just an aside. So with this, you can show that the normal ordered Noether charge takes this form. And now you can explicitly show. So in the classical theory, we knew that this was 0. And now in the quantum theory, you can show that this indeed is true. Um, and this was in the classical theory was very simple because we knew that dq dt was 0. And this you can explicitly compute using the ladder operator expressions for q and also for h. If you do that, you indeed get it to be 0, which is consistent. There's a question, how charge can be an operator. Uh, so charge is, so just like position and momentum are observables in your quantum theory, and we know that observables are they map to operators, observables which are in classical physics as just functions, they map to operators. So you can measure the charge of your particle in the lab. So charge will be also described by a operator. In fact, a Hermitian operator, because the physical quantity will have real eigenvalues. So that's why this part is just uh, quantizing your theory. Okay. So when we promote everything to operators. So that's how charge is an operator. Just like position and momentum are. Now you can show that this is commutes with the Hamiltonian. So this means that you can simultaneously, so recall from your quantum mechanics knowledge that you can simultaneously diagonalize mm, these Q and H. Okay, so you can find a simultaneous eigenstate for Q and H. Let's say you look at the energy eigenstate, which are eigenstates of the Hamiltonian. So they'll also be the eigenstates for the Q, for the charge operator. So now let's, using this, we can now compute. So at times I will not denote this normal ordering, but keep in your mind that things will always be normal ordered. So as to remove this vacuum 0 point energy, which was divergent. Okay. So if you now apply this on the vacuum, you will get just 0, and that should be clear from here itself that these annihilators will kill the 0. So the vacuum is neutral. So this implies that the vacuum is neutral. And if you act it with the A excitations, then you will get a +1. Again, these are all vectors. I might miss that at times, but remember that this ladder operator, the level is a 3-vector K, and you act these on the B's, then you'll get a minus sign. Okay, again, that should be clear because you see the B's, they come with a minus sign here. Okay, when you compute the charge operator in terms of the ladder operators. So this means now we have uh, shown that the charge of the A excitations is negative of the charge of the B's excitations. Okay. Uh, so further, you can do another exercise that if you take the momentum operator and you write it in terms of the ladder operators, just like we did for the Hamiltonian. So you know the expression of the momentum operator in terms of the stress tensor. So recall uh, this was written as d3xt0i. So now you know the stress tensor in terms of ladder operators, and if you do that exercise, you can write P in terms of the ladder operators, and this will just spit out as the momentum of the state K. Okay. So P acting on the state gives you just Ki. And similarly, for the B, similarly, this state will have momentum Ki. So when you do this, now this justifies, which we had promised to show, that indeed this quantity was rightfully called the momentum. Okay, because as you see, it spits out the eigenvalue Ki, which is the momentum of this state. And yeah, so what we saw is that, so let's quickly summarize that the vacuum was neutral with 0 energy and 0 momentum. these states were positively charged, so +1 charge with omega k energy and k as their momentum. And these states were exactly similar to the A states except the eigenvalue of the charge. So their energy and the momentum were the same, but their charge was different. And this is what is said that if A level particles, then B's level antiparticles. Okay. I should actually say A dagger and B dagger with the level K. So this is what will be the definition of particles and antiparticles. And in a few moments, we will see that uh, recall we had this charge conjugation, phi to phi star, and we said that uh, reverses like maps particles to antiparticles and vice versa, and that we will see is consistent with this definition. Okay, so we will discuss this symmetry in a few moments, but for now we will say that the charge eigenstates with +1 charge are particles, and the other are what will be called an antiparticle. And other than the charge eigenvalue, they have everything else similar, like the mass or the energy, in this case, the momentum and all of these things. So this is why you would have known that when we say electron and anti-electron or positron, only the charge changes. Rest all like the mass and every other thing remains the same. So this is like the first uh, thing about antiparticle that you learn. Uh, Now, once we know this, now let's talk about how to create uh, multi-particle states. So this is all we talked about single particle states. So now let's create multi-particle states. So a general multi-particle state, we can write it like this. Vectors P1 to P N A and Q1 to Q N B. So I'm denoting the states by their momentum level, P's and Q's. And this, as you can imagine, will be like A dagger, P1, A dagger, PNA, then B dagger, uh, 1, sorry, Q1 to B dagger, QNB, acting on the vacuum. Okay. And the A's will count your particles and the B's will count your antiparticles. Okay. So a general state in momentum space looks like this. And the net charge will just be Na minus Nb. Okay. So number of particles because they are plus charge and number of antiparticles which are minus charge. And the net Hamiltonian is just the sum of energies. Okay. So these guys will have omega pi as energy and the antiparticles will have omega qi. Okay. Mm. So that's it. And this generic state lives in a space which is called the Fock space. Okay. So which is essentially like so the Fock space is like a generalization of the Hilbert space that you are familiar with quantum mechanics, where the particle number remains conserved. But here, as you see, that so this is a generalization of the Hilbert space with conserved particle number that you have encountered in quantum mechanics, but now allows for particle uh, number not generically conserved. Okay. And we see that that's the case. Like you can have two particle states with just two oscillators acting on the vacuum, or three particle states with three oscillators acting on the vacuum, and all of this uh, together, taken together, is what is called the Fock space. So as we started earlier, and we said we had this heuristic argument that if you try to include relativistic principles with Heisenberg's uncertainty. So like the E equals mc square with del q del p greater than equal to h over h bar over 2. We said that there's something called a Compton wavelength. It means that if you try to look at a box whose dimensions, let's say, are less than that, then you will have a plethora of particle-antiparticle pairs. And this is exactly what we now constructed. From in the formalism of QFT, that we indeed see that the uh, physical space where we are doing computations doesn't have a conserved particle number. So, and it has these particles and antiparticles popping up. Okay. So now let's talk a bit about uh, statistics. And so the statistics, these guys, these momentum states, they satisfy these, yeah, these momentum excitations, they satisfy. So for this, let's look at a two particle state. So a two particle state would just be P1, P2, and this is just a P1 dagger, a P2 dagger on the vacuum. Now note that because of the commutation, the daggers, they commute. So you can exchange them like this, and you will end up with something like this. Okay, P2, P1. Okay, all of these are vectors again. Yes. So you see that because of the commutation relation that we had, and because the dagger operators, they commute, so that's why we get that P1, P2 is P2, P1. So if you exchange two ladder operators, or if you exchange two particles, then you do not, you essentially get back the same state. So if a state had P1, P2 and you exchange the particles, you essentially got back the same state. So these particles uh, are what are called bosons. And we will, in an exercise that I will set for you, you will see that these guys will have spin 0. Okay, we haven't yet defined what is called spin, but whatever that word spin is, we will define it today. And you can see that it will be an operator, let's call it J. So if you act J on this state, then you will see that it has spin 0. Okay. So we see that this exchange of particles, which obeys these commutation relations, we will see that it actually leads to spin 0 particles. And then later, like next week, we will see that when instead of commutators, we'll have anti-commutators, we will get what is called spin half integer particles. Okay. So half integral spin particles, and which will be called fermions. So we will define this spin today, whatever this spin I have put under quote unquote, and then there will be an exercise that you will compute it in terms of ladder operators, and when you act it on a state, you indeed get the spin to be 0. Okay, so now you see that we have been calling these particles, and there was a question last time, yesterday, that what about the position space excitations? So now we will look at position space excitation. So these are all momentum space excitation, but we still call them particles. But normally we are used to think of particles as excitations in the real space or position space. So let's discuss that now. There's a question in the chat. Is Hamiltonian conserved in this Fock space? Yes, because the theory is Lorentz invariant. So the Hamiltonian that we constructed was a Noether charge for the time translation, and by Noether's theorem, it's conserved. Okay. Is there and that's why this q is also a conserved quantity, right? So when we say in the quantum theory anything that is conserved, then it essentially means that it should commute to the Hamiltonian, which it indeed does. So not only h but q is also a conserved quantity. Is there a dynamic for popping up particles? I don't know what that means. Okay. Okay, now let's move forward to position space excitations. So recall that we had pi as an integral over the momentum space, and I'll skip the explicit details, but we wrote it as a k and some exponentials and b k dagger. Okay, and now we can just act it on a state, and that will give us again the same momentum factors, but the interesting structure that emerges it is this, and there's an exponential acting on 0. So we see that this is what this does is creates a B excitation uh, localized at xt, at the position xt. So, and if you do phi dagger xt 0, then you will get that it will create again something of the integral measure times an exponential, but with the a's. And that just follows from the expressions of phi and phi dagger in terms of the ladder operators. So this means that the phi's, they create antiparticles in the position space, and the phi daggers, they create particles. Okay. And that's just a consequence of the expression for phi and phi dagger in terms of the ladder operators. And now we do this interesting thing that now recall, as I mentioned briefly, that C takes phi to phi star, which means in the quantum theory, this goes to phi dagger. And that's exactly what happens between them, like an exchange of particles and antiparticles. So as we said, phi creates antiparticles and phi dagger creates particles. So this is in line with the charge conjugation, this discrete symmetry. So this discrete global symmetry of C taking phi to phi dagger. So this maps particles to antiparticles and vice versa. Okay. Uh, so what we defined as antiparticles as the excitations from the oscillators B are mapped to the excitations oscillators by the oscillators of A. And this is indeed the swap of phi to phi dagger, which, so that's another way to understand particle antiparticle construction, that they're mapped to each other under this discrete transformation. Okay. This discrete phi to phi dagger. And now, as an exercise, you can check that if you just have a real scalar field, then charge conjugation just maps phi to phi. And so here, a particle is its own antiparticle. Okay. And this, if you remember, is tied to the fact that the B's oscillators, they satisfied a nice condition that this is tied to the fact that these B's that we defined, they were nothing but just a dagger. Okay, so when you would have solved the simple harmonic oscillator in the classical picture, this is just saying that B is A star. So a particle is its own antiparticle when you are just looking at the real scalar field. But in the complex scalar field case, there is no such uh, relation. This is violated, okay? Because generically they are independent oscillators. And you should always keep in mind that this is different from the discrete symmetry that in the real scalar field we had considered, the phi to minus phi, okay? That was totally different from the charge conjugation. So the charge conjugation symmetry in the real scalar field case is just like an identity. So this is like an identity transformation. So it takes the field to itself. Okay. So that's why when discussing discrete symmetry case, we discussed something that was more interesting. Doesn't just check phi to phi. But from the charge conjugation point of view, now when we discuss particles and antiparticles, there indeed exists such a thing for real scalar field, but it's just a trivial transformation. It just maps the field to itself. Okay. Now let's see what, yeah. So now as promised, I will define for us what is the spin. So recall that we had this, so when we studied the symmetries under arbitrary Lorentz transformation, so we had gotten a conserved current, which was written like this. And the Noether charge for this guy again will be just J0 rho sigma. And this object and the eigenvalues of this object in the quantum theories. So in quantum theory, so this becomes an operator in that sense. Sorry. So when you promote it to operator with J0 rho sigma, this is what we will define as spin. Okay. So when we promote this object to operators and we uh, uh, now take this generator that was generating infinitesimal Lorentz transformation. So essentially, when your theory is invariant under rotations and boosts, so that operator, when you evaluate it on state, the eigenvalues that you get, just like when you operated uh, acted the charge q, the Noether charge q for the U1 symmetry on a on a momentum state, you got +1 or -1. So when you do this on a state, the eigenvalue that you will get will be called spin. And then you can show explicitly that both in the real and the complex, so this is an exercise, complex scalar field case, uh, these eigenvalues of this quantity j hat will be 0. Okay. So which means these will what will be called spin 0 particles. And when we do move to the Dirac field, we will see that it will have spin half integers, okay? Half, three halves, or something like that. And as we saw, so just to summarize, we saw that these particles were bosons, what we call bosons. They satisfied commutators. They had a commutator relation, and they had spin 0. So this is something that we saw, and the missing piece is this exercise that when you do, you will realize. And next time, I mean, next week, we will see that what we will call fermions. And the fermions means that, yes, this 0 means the time part. Okay, so T, X, Y, Z is X0, X1, X2, X3. Okay. Uh, And this should also be clear from the fact that whenever we are talking about Noether charge, we integrate the time component of the Noether current. So hence, it has to be that if I'm calling it a charge. Okay. So this is a statement that we saw that bosons, the satisfied commutator relations, and hence when you swap the momenta, you just got back the same state. And these are also spin zero. Now, we will show in the Dirac case that so in this case, these are spin zero, uh, but because this is a scalar field. Now, okay, so there is a question in the chat, so I'm addressing that. So the question is it spin zero or integer spins? So what we dealt with, that's the scalar field that will have spin zero. But when you will do quantum electrodynamics, that's a vector field, you will get spin one. Okay. So they will also be called bosons, okay? But this is a special class of a boson, which like zero is still an integer, but we won't discuss spin one particles. We'll just discuss spin zero and spin half. Yes, so as I was saying, when we do the Dirac field, there we will see that we will get spin half. We will have anti-commutator relations, not commutators, and we will call them fermions. And all of this follows from just so let's say what input did we use in this whole story. We just used that our theory has to be relativistic, and that defined for us what spin was, which was the eigenvalue of generators of eigenvalue of the charge for the Lorentz transformation generator. And we used commutator relations, which is essentially saying imposing Heisenberg uncertainty relations. So when we try to make contact, especially relativity with quantum theory, spin comes out from it. And it also dictates what kind of statistics will be obeyed by these momentum leveled eigenstates, or if you like, the wave functions. Okay. So at the moment, we just saw one part of this, that what happens when you have commutator relations and spin zero particles. Next week, we will see what happens when you have the other side. And we will do a simple exercise where if we force those particles to have commutator relations, then it will lead to something bad. Specifically, it will lead to the Hamiltonian, the total energy being negative and not having a lower bound. So hence we will be forced to take anti-commutator relations. So we will see all of this explicitly. Okay. Now the one final thing before we move to propagators is something called operator value distributions. So what do I mean by that? So note that though we have been using these operators A hat and A hat dagger, their commutators. For instance, if you just look at the expectation values of this quantity on the vacuum, then you can show that from the commutator that they satisfy, that this indeed just give you a delta function. Okay. And as we know that all of these commutators, these A's and A dagger commutators, they always involved these Pesky delta functions, right? K and K prime. So K minus K prime. And as you might be knowing, this is actually not a function in the strictest sense, but this is what is called a distribution. Okay, so that's why people call it that this is like a Dirac delta distribution and not just a Dirac delta function. So what do they mean by that is in physics, when you do computations with this, you get this pesky delta function floating around. And this is again tied to these facts that you have this infinite degrees of freedom and this zero vacuum energy which just goes to infinity. So we talked about one prescription to deal with this. So that was normal ordering. And now we'll talk about another prescription which is called smearing. Okay. So what is smearing? So to understand smearing, uh, you can do a couple of exercises first. And again, these are very trivial once you write every operator in terms of the ladder operators. So if you again take the scalar field case and you just evaluate this, you will see that this is 0. And but if you evaluate uh, the 2-point correlator, then you can show that this goes like an integral like this, and which just goes to infinity. Okay. So, and again, if you recall, this is exactly the 0-point energy of the simple harmonic oscillator with level k. So this is an exercise, you check that this holds true. So we see that these operators that we are dealing with, these position space operators phi's, so they are not very nicely behaved if we just naively compute these 2-point and 1-point correlators. So there's a way to regulate this and get rid of these uh, infinities. So this is a second prescription, and that is to consider uh, again a state uh, which in momentum space will now look like this. So the usual thing, but now you have a factor which I will explain in a moment what it is. So I have plugged in this guy, which can be taken as a Gaussian wave packet, okay? Something like this. So this is like a Gaussian wave packet. And which is localized both in position and in momentum space. So essentially what this does is, so recall that a Dirac delta is a function that's peaks at your infinity, okay? At peaks to infinity at the origin. So you can smear this. So when I say smear, so I am considering a wave packet where you expand the width a bit, and then later you can take this width, let's call it epsilon, to 0. Okay. So this smearing or expanding the width to give it a finite width and prevent it from going to infinity is essentially done by this kind of a test function. Okay. So I'm calling it a test function analogously as, like, when you would have studied electrodynamics, there were test charges. So what are test charges? So these are probe charges which don't interfere with your electric field but just measure its effect. So similarly, this function is harmless in the sense that imagine any computation that you do in a lab, your detectors will always have a finite spread or a finite width. Okay. You cannot measure the position or momenta or any observable to to infinite degrees of accuracy, and that's because you will have some scale coming from the detector itself. So this procedure ensures, or this procedure captures that scale, if you like, the scale that you can never get away of a physical detector. So smearing essentially does this, that it removes this infinite accuracy problem, which is also tied to this infinite vacuum point energy problem. And it mathematically what it does is it spreads the delta function so that now it's well behaved for computations, and later you can take it to 0. So you just normalize, or you act the state with a wave packet of a finite width. You can choose your favorite function here. So one example is this Gaussian wave packet. But essentially the idea is this, that because in reality we will be measuring things with finite spread detectors, so which have a inbuilt scale in them. So hence you are allowed to smear it. So that's why the word smear. Okay. So that's another way to deal with these pesky deltas and these infinities. And yeah, so we learned two ways to deal with these divergences in QFT. There is a third way which we will study in interacting theories. So I'll just mention it for completion, which is called renormalization. Okay. And this is going to be very important, which you will learn in interacting QFTs in the next set of lectures. But okay, so all of these are ways to deal with infinities. Now let's move on to the main content of today's class and the propagators. Okay. Okay. So as you might recall that when we began this QFT lectures 2 weeks or 1 week back, so we first computed something that was called a propagation amplitude. So we said if we have a particle here and then what's the probability that we will measure it at some other point. And then we tried to use the relativistic version of the energy. So instead of uh, this thing p square over 2m, we used the relativistic version, and we then computed that integral, the propagator or the amplitude of the propagation. And then we found that when these two distances were space-like separated, that propagator was still non-zero, which means that there is a non-zero measurement that you can do even for space-like separated points or outside the light cone of one of the particles. And then so that means that we said that naively this means causality was being violated. So the content of the next 1 hour and 15 minutes will be to redefine the notion of causality and use what we have learned till now to argue that even though that happens in QFT, we can still have causal propagation. Okay. So we will see all of these things. But I just wanted to start by saying that we have already done a propagator calculation in the beginning where we saw that this propagator, so let me call it P, this propagator x and x prime between space-like separated point was non-zero, okay, for x minus x prime square negative, which is space-like separation. So now we will, in this next hour, we will see how to restore the notion of causality, because that's something that we have not done. So we need to make sure that our theory is causal. And while doing that, we will also restore causality for another reason. And that is, remember that we talked about the Hamiltonian description when we quantized our theory. So the Hamiltonian description involved defining what's canonical momenta, which for real scalar field was just this phi hat, and this led to us picking a time coordinate, right? So in all of the Lagrangian part, everything was written covariantly, but in the Hamiltonian, we picked a time coordinate. So again, I said that now one could argue that we might have broken causality somewhere while we quantize the theory, but as we will see, that's not the case. Even if we pick a time coordinate, intermediate steps they do break causality, but when we write down anything that is relevant for computing observables or things that you measure in a lab, those will come out to be Lorentz invariant and with restored causality. So that's another reason why we will study how to restore causality in this case. So one is to have a new notion of causality that doesn't contradict with this fact, and another is to further explain that Hamiltonian prescription and the quantization where we selected a time coordinate indeed didn't give rise to something weird that breaks our notion of causality, because that's necessary, because at the end of the day we want to build a relativistic quantum theory. That's what we started with, right? Okay. So in order to do that, let's look at an integration. So you see that if I consider an integration like this, k square minus m square, where k square is k0 square minus k square. So k square minus m square, you can write it as this, okay, where omega k square is the quantity that we had defined like this, okay. So we started with this integral. So that is an integral of a delta function. And recall that in this integral, this is Lorentz invariant, because that's just the integration measure for 4 vectors. And this argument is again Lorentz invariant because that's a scalar. That's a scalar product. Okay, that's like the line element. So this means this whole integral is Lorentz invariant as it stands. Okay. But note that we had been using integrals like this, uh, when we are integrating over momentum space. And now we need to argue that these are also Lorentz invariant measure. Okay. So that's what we will do now. So a variant of these three-dimensional integrals are also Lorentz invariant. That's what we will show. And if we show that much, then we will be relieved that our theory is still causal, even after this picking a coordinate time and all that business. So that's why we start with this integral, which is manifestly Lorentz invariant. So this is by construction Lorentz invariant. And from that, let us show that indeed these three volume integrals we were doing are also Lorentz invariant. So let's see how to do that. So now we break it up into the space and time part. So d3k, dk 0, delta k0 square minus omega k square. Okay. Now you see the k0 will satisfy an equation plus minus omega k. Okay, so when you just take the square root, you will get two branches, the plus and the minus. Now we will use, so the idea will be to first evaluate the time integral. Okay, so to do that, we will use a delta function identity. And don't worry if you don't know this, there will be an appendix where this will be proven. So the identity is this, that you evaluate the delta function on a function fx, then you sum it up over all x's where the function is 0, and it gives something like this. Okay, x prime minus x over f prime x. Okay, so there's a delta function identity that says that if you evaluate the delta on the roots of the function fx, so this means all the points where fx is 0, its roots, so then it factors into sums of the trivial delta function over the derivative of the function at exactly the roots of the functions. As I said, you will find an appendix in the notes where this will be proven. So with that identity, what we can do is break down this piece k0 square minus omega k square as delta k0 plus omega k over 2 mod omega k, 2k0 plus the other root k0 minus omega k over 2k0. Okay, so recall that there was an integral over overall. So we break the thing like a square minus b square as a plus b and a minus b. So those are the two roots here. So using this relation, we break it to two parts. So and f prime here in this case is just 2k0. So that's f prime. So that's why you get the denominator is 2k0, and these are the two factors. And then you sum them using this identity. So I hope that's clear. So with that, now we can evaluate the integral. So that implies this integral is now a sum of these two integrals, and that will just boil down to this. Okay. And the reason is, so you see k0 was plus minus omega k, but as we know that we have picked, so k0 is like the energy, right? E. So E is omega k. So this means we will pick the plus root here, and that would imply that you indeed get this part. Okay. So that means this quantity that we got, that d4k, k square minus m square, and by all these arguments that we did, we finally ended up with this integral. Okay. And since to start with, this guy was Lorentz invariant, we ended up with something that has to be Lorentz invariant. Okay. So this proves that this d3k integration that we were doing, that is indeed a Lorentz invariant measure. And this recall that this factor is very crucial. So just this quantity won't be Lorentz invariant. So because of this 1 over 2 omega k, which was also the expression you saw in the ladder operators, so that was necessary to argue that this three-dimensional integral is also Lorentz invariant. I hope the steps are clear. So because it could be new for some of you. So let me repeat. So what we did was we used this identity to split the roots of the delta function acting on the function like this to a plus b and a minus b. And then we picked a particular root, let's say the plus, because that's the convention for energy being h bar omega k. So h bar is 1 here. And that gives you that you indeed get the integral to be this. Okay. So that proves that this is a Lorentz invariant measure. Okay. Now let's talk about the commutators. Sorry, the propagators. So we recall that we had such a commutation relation phi of xt comma pi of yt. So we imposed this commutation relation when we said that we will quantize the theory. So it amounted to imposing this commutation relation at equal times. And now let's try to see what happens to this object. So what happens to this object? So let's see what happens to this object when we look at space-like separated points. Okay. And that will lead us to a notion of causality that we will need. And for the manipulations, we needed that this guy was Lorentz invariant. So we first used that so we first proved that this three-dimensional integral is Lorentz invariant, and now we will put it to use. So let's go ahead and compute this quantity. And then we will tie it to the particle-antiparticle picture, and we will say what this new notion of causality is. Okay, so bear with me. At this moment, it might feel like I'm doing computations after computations. So we will summarize all of these things nicely once we do the computations. Okay. So recall that, uh, sorry, I did something wrong here. So this is indeed the commutation relation that we had. But what I wanted to say was, uh, let's say what happens to this essentially was not the commutator I was writing above, but a commutator like this. Okay. So I'm interested to see what happens to this commutator Uh, so that's just the, so this is just the relation that we impose. But now we want to see what happens to this commutator when we look at space-like separated points, okay, x and y. So now let's go ahead and compute this quantity. And we have everything in our tool to do this. So recall that phi was expressed in terms of these fields A and B daggers, and phi dagger was expressed in terms of the fields A dagger and B. So I'm now schematically just writing it in this way. So you already know these expressions. So if you plug them here, so let's call this star 17. So plug these expressions in star 17. So if you do that, you can write phi x and phi dagger y is an integral like this. Again, this is straightforward. You just have to plug the relations. 2 omega k e to the power minus I k dot x minus y minus e to the power plus I k dot x minus y. Okay. Let me write this a bit nicely. So that's the, so that's what it becomes. Okay. Now here, this k dot x minus y in the exponential is just the Lorentz invariant scalar product, which if you expand is just this minus the vector x minus y. Okay. So now note that even though these intermediate steps were not Lorentz invariant, if you recall in their definition, they involved an integral with a 1 by root 2 omega k factor. Okay, there was some integral like this. But this is not Lorentz invariant. What was Lorentz invariant was this thing with no square roots. And that's why when you do this thing, now you see that these guys, these exponentials are perfectly Lorentz invariant because it's the Lorentz scalar product. And this integral that we argued, this measure, just we argued before, is also Lorentz invariant. So hence this quantity, this whole quantity is now Lorentz invariant. So that's nice. And this is what I meant when I said that when we quantize the theory, the intermediate steps like expressions, so individual expressions for these phi's and phi daggers involved the square root. So they were not Lorentz invariant, but this commutator is Lorentz invariant. Now let's see, go ahead and commute this and see what it gives us. So this is why we did that computation of proving that this was Lorentz invariant, right? Okay. Now let's look at first. So point one is, so case one is like time-like separation. So time-like separation means x minus y whole square is greater than 0. Okay. So if you look at time-like separated points, you can imagine doing a Lorentz transformation on such a point so that you put all the dependence only on the time part. Okay. So this is just like saying that like in ordinary rotation, this is just like saying you look at a vector like this, which let's say I'm in 2 dimensions, so y and x. So you look at a vector which has both a y piece and a x piece. But now what you can do is you can rotate your coordinate, and in that rotated coordinate, you can just put everything along y, right? So it just becomes E y prime in that rotated frame. So this is why in the analog of Lorentz, the Lorentz version of this is if you have a time-like vector, you can do a rotation. But in this case, rotation will involve space and time. So essentially like a boost. And you can land up with a frame where all the contribution is directed along the time axis. So like this, okay? And the space components are 0. This is exactly the Euclidean version, but done in the Lorentz way. So if we do that, now let's evaluate this quantity. So let's denote this quantity as I tilde. So I tilde, uh, red probably is not a good color. Let's write it in green. So I tilde, observe is this quantity, this integral. So when we are looking at a time like vector like this, so you can write I tilde as like this. So 2 omega k, and only the time parts will survive, because the space parts we have rotated our frame to put them to 0. Minus e to the power plus I omega k x0 minus y0. And this, now you can see that you can write it in terms of a sine function. So sine of omega k x0 minus y0. Okay. And this is not equal to 0, because if you integrate this for the sine function, you can show that this is indeed non-zero. And this you can integrate if you want. You can do this as an exercise. And one of the hint here will be to go to polar coordinates. Okay. So if you go to polar coordinates, you can express this measure d3k as k square some cos factors and dk. So with that, you can perform the integral and you will find that it's non-zero. Okay, so for time like separated points, this thing is non-zero. Now let's look at case 2, when you have space-like points, space-like separation. Okay, so when we have a space-like separated points, then again we can do a Lorentz transformation. So space-like means this is now less than 0. Okay, so now we can do a Lorentz transformation where we can put everything in the spatial parts. Okay, so this is again rotating in such a way that you only pick out the non-zero spatial parts and the time part as 0. So this is a purely spatial vector. And now let's exactly do the same integral. And if you do that, you will end up with something like this. So this is what we call I tilde 1 by 2 omega k e to the power plus I k dot x minus y. So now we are picking the spatial parts, okay? Exactly like we picked the temporal parts before. Okay. Now, but there is an interesting thing that we can do. So this is what we get. But now we can do something interesting. And this is related to a very nice question which was asked in the beginning. Delta, sorry, I'm just looking at a question in the chat. Is it all about? Yeah, delta 3 isn't Lorentz invariant. So the question is, delta 3 is not Lorentz invariant. So if you have a delta 3, that's not Lorentz invariant. But we started with this expression, right? K square minus m square. And this is Lorentz invariant. Okay, and that's what I started with. But yes, delta 3 is not Lorentz invariant. You are right. Okay. So now moving on. Yeah. So yeah, sorry, I was forgetting. So in the beginning of the class, we there was a question about what are space and time intrinsically, and I said that they are essentially coordinates. You treat them at the same footing. But one major difference is in the light cone that you are interested in, time can only move forward, but space can move both left and right. So space is bidirectional, but time is unidirectional. And because space is bidirectional, what you can do here is you can relabel k to minus k in this part. And if you don't believe, you can perform a quick check. So you check that if you do this, then this second term with this measure d3k over 2 pi cube 1 to omega is invariant under this k to minus k. So the omega part should be clear because omega minus k is just minus k square plus m square root over. So that is indeed omega k. And similarly, you can show that this measure is also invariant. So if you do that, and the understanding was because space is bidirectional, why always second term? No problem. You do for the first term. If you do for the first term, we'll pick a minus sign here and they will cancel. If you do for the second term, you'll get a plus sign here and they will cancel. So it's not just that y for the second term only. Okay, you can do it for anything. No, 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 no. If your question is the first term is not affected, yeah. See, these are two separate terms. Okay, I tilde, you can write it as I1 and I2. Okay, and the way we wrote it, this guy came with a plus sign, the I1 part. Okay, let me explain this a bit slowly. And this guy came with a minus sign. Okay, this is what we got here before doing the relabeling. Now, you see, these are independent terms. The I1 term is independent of I2 terms. In other words, you are summing over, so you are integrating over the whole k, right? Now note that I1 was a k integral and then this factor, and I2 was also a k integral. Now you can, because these are integrals, you can call it k prime. Okay, so k prime here and k prime here. That's fine because these are dummy indices. You are integrating over the whole thing. At the end of the day, no k will be left. So hence these two are independent of each other. So what we did was we performed a relabeling here. And when we did that, we flipped this minus to plus. But one could also perform the relabeling here. If you do that, you will flip this plus to minus. But the key point is you just relabel one of them, not both of them. If you relabel both of them, you will again get the same integral with opposite signs. But that will not help you to solve the problem. In order to solve the problem, you relabel one of them. And why that step is justified? Because these two are independent integrals. You're integrating over the whole three momenta. So this level of three momenta is like a dummy index. In other words, if you write a mu b mu, you can call it a alpha b alpha, which is essentially saying that you can integrate over k prime in the second integral and k in the first integral. So k is independent of k prime. You can do that. But the trick is to independently only relabel one of them, not two. And hence they cancel. Okay. So I hope that's clear. So that's why you get a big zero for the integral. Right?
But why can you relabel one of them and not the other one?
No, no, you are free to relabel both of them. But if you relabel both of them, you are not solving the integral. Okay? It's still an integral, but you don't know what its value is. In order to obtain its value, you relabel one of them. You are always free to do relabeling anything that you like because you are integrating over the whole volume. But that will just give you again the same integral. But you didn't evaluate it. In order to evaluate it, you just relabel one of them. It's just an evaluation trick. I'm saying the evaluation, the relabeling is justified because they're independent integrals. Okay?
Okay, okay.
I mean, was that clear?
No, that's clear. Yeah, I need to think about it.
It's something like this. Okay, I get why it could be confusing. It's something like this. Let's say you are integrating an odd function. Okay, so f of x dx. Okay, what do? We split it into two parts,
Mm.
f and then 0 to infinity f. Okay, and then what we do? We take x to minus x. Okay, and then we use this property. We take x to minus x. Okay, and then we use this property. We take x to minus x. Okay, and then we use this property. We take x to minus x. Okay, and then we use this property. We take x to minus x. Okay, and then we use this property. We take x to minus x. Okay, and then we use this property. We take x to minus x. Okay, and then we use this property. We take x to minus x. Okay, and then we use this property. We take x to minus x. Okay, and then we use this property. We take x to minus x. Okay, and then we use this property. We take x to minus x. Okay, and then we use this property. We take x to minus x. Okay, and then we use this property. We take x to minus x. Okay, and then we use this property. We take x to minus x. Okay, and then we use this property. We take x to minus x. Okay, and then we use this property. We take x to minus x. Okay, and then we use this property. We take x to minus x. Okay, and then we use this property. We take x to minus x. Okay, and then we use this property. We take x to minus x. Okay, and then we use this property. We take x to min let's say on this part, and then we get an overall minus here, and that cancels this part, right?
Mm-hmm.
You could do the same
Yes.
with both, but why do we do it only with one part? So is to cancel it, so is to evaluate it.
Yeah. Yeah.
Here you could have argued that let me do it on both, but if you do it on both, you are still left with this integral.
You get the same thing back.
Yeah, exactly. So you don't evaluate it. So the actual question to ask here is the relabeling independently correct? And the answer is yes, because these are independent integrals. Okay,
Mm.
good. Nice. So
Thank
uh,
you.
no worries, no worries. Thanks for the questions. Yeah. Okay, so where was I? Sorry. Yes. So we get a big zero for this. And this is for space-like separations. Okay. Uh, Now let's try to argue what causality and everything is. Let me remove this. That's a trivial result you know about odd functions. Okay, so we will define that uh, we will define a notion, a new notion, and we will see how it fits into what we know. So the definition is what is called microcausality. So at space-like separated points, fields like phi x and phi dagger y, they commute. Okay. So because they commute, so you can independently work with them when they are space-like separated. And now we will see that how this ties up nicely to the particle-antiparticle picture. But let me give you a notion, sorry, let me give you an intuition why this is the definition that we are taking. Now imagine that, so for that, let's look at quantum mechanics. We know that xi and pj, they don't commute, right? And this is why we say that they are not simultaneously, we used to say that they are not simultaneously diagonalizable, or you cannot measure momenta with 100% accuracy and or position with 100% accuracy simultaneously. Okay, you can always have some inaccuracy built into this. So you see that you cannot do a perfect momentum measurement without affecting the position measurement and vice versa. So x and p, non-vanishing commutator, means one of the measurement affects the other measurements. However, today we saw that this charge and the energy eigenstates, they were identically zero. And we said that they are simultaneously diagonalizable. What that meant was you can do independent measurements on the charge and independent measurements of the energy, and that's fine. So that's built into this notion of microcausality. So if at space-like points, commutators they vanish, then they don't talk to each other. But if they don't, and obviously for time-like separated points, as we saw, for time-like separated points, as we saw, this commutator was not zero. Okay, when they were time-like separated. So that is analogous to saying when you were measuring momenta, you also affected position or vice versa. So you cannot independently measure these things. So they influence each other. So that's the meaning of causality now. That space-like separated fields don't influence each other. So their commutator is vanishing. Whereas time-like separated fields will influence each other. They live in the same light cone. Okay. For instance, if you want the light cone picture, so if this is my light cone, then there's a point x here where phi lives, and there's a point y here, and they're time-like separated. So hence they will influence each other. And this notion can be understood from vanishing of commutators and non-vanishing in the quantum theory, and how measurements affected each other or not. So that's how this is built into this. Now let's see an example that an instance that nicely pairs this up with the particle-antiparticle picture. Okay, so this is what we will see now. So now I have just motivated you this definition from quantum mechanics, but now let's unpack exactly what this definition tells us. Okay. So this is just an analogy or a motivation, but now we will concretely see what it does in QFT. Okay, an analogy or a motivation. But now let's see concretely what it says in QFT. So I hope the analogy is clear. Now let's move on to this thing. So now this is something that we have already done in the first lecture, but let's do it now in this Lorentz invariant way. So recall that in the first lecture, we had computed something like this, but using the Schrodinger equation and plugging into it the relativistic energy, but now we will do in QFT. So let's say you are interested to compute this quantity. Okay. This is exactly the quantity that we computed in first lecture, but just from Schrodinger equation. Now we are doing it for complex scalar field. So let's see how to compute this. So recall that phi xt, when today we discussed position space excitations, we said this creates antiparticles. Bk dagger and some E acting on 0, and its conjugate could be written as this thing over to pi k bk with a different exponential now. And these exponentials are different. You have to take I to minus I. Okay, so when you do that, and then you can plug it in right here. So let me call this I prime now, the integral. So we are interested in computing I prime. So if you do that, you will get pi dagger y phi x as d3k1 over 2 pi cube d3k2 over 2 pi cube and 2 square root omega factors with k1 and k2, and then e to the power I k1 dot x minus I k2 dot y times this commutator bk1 bk2 dagger. Okay, and now you can use the explicit commutator relations of the b and bk to write this simply as, so you can evaluate this to write this as this e to the power I k dot x minus y, where, let me stress again, this is the 4 vector inner product. Okay, again, as we see, intermediate steps were not Lorentz invariant, but the final step is. So this is Lorentz invariant, this is Lorentz invariant. Okay, now this is something that so now we will you can compute this integral, you can evaluate this integral using complex analysis like in the first class we did. So you will have to pick these the square root, just like the square root branches we picked, the branch cuts. And I won't do this here. Again, I'll write down an appendix for this. You can show that this I prime goes like e to the power minus m x minus y for large x minus y. Okay. So space like. And this is something I am going over a bit fast because we did an analogous computation in the Schrodinger equation. That exact complex analysis method we'll follow here. And there also we got it to be non-zero, and here also we get it to be non-zero. So even in the full relativistic setting, this propagation amplitude is non-zero for space-like separated points. Okay. but now we will argue that that's still fine. Okay, we will argue that next. So before that, let's try to understand what this is saying, what this means. Okay, and that will be key to understanding this notion of microcausality and why everything still remains fine. So here I am using a notation. So let me briefly mention that. So normally when I will write an expectation like this, I will mean it to evaluate on the vacuum. Okay, so here I am not explicitly mentioning that it's evaluated on the vacuum, but that's what I will mostly use. Now, this non-vanishing nature of I, so I prime not equal to 0, is what is called vacuum entanglement. Okay, and let's understand how very briefly. So recall that in the first lecture there was a question by someone as to will we see entanglement. So this is what we will see now and try to understand it, why this non-vanishing is tied to entanglement. So let's say that you have two regions, region A and region B, and let's say that they were space-like separated. And let's further assume that the total vacuum could be written as a factorized in a factorized way like this. Okay, so all that this means is you can independently factorize your space into region A and region B. Let's say this is the case. Let's assume this is the case. Okay, I'm not saying this will always be true. I'm saying assume that you can factorize your theory nicely. So in the Hilbert space language, if you like, it means that you have two Hilbert spaces that don't talk to each other. Okay, they're nicely factorized and separate. So if that's the case, then if you compute the expectation value of any operator in the region A with an operator in region B, then because of this factorization property, these will separate into something like this. Okay, and that's because again because of this factorization property, because everything like your vacuum and all your states, they factorize nicely into H, into things that live in HA and things that live in HB, and they don't talk to each other. These are mutually like independent things. So that means if you write a 2-point function of like write an expression like this, it will nicely factorize into its A part and its B part. Okay, so I hope this is clear. Here I am just using this property. Okay, these two properties that you factorize them separately. Now recall that we had argued that where did we argue that? Just give me a moment. So when we talked about smearing, we had this condition. Sorry, I'm going a bit up here. Yeah, we had this. Where did that go? Yes, we had this condition that for phi, uh, the 1-point function, which is just the expectation value of phi in the vacuum, that was 0. Okay, this thing. So let me call it star 20. So that was a result you can show when you write phi in terms of ladder operators and act the vacuum on it. So since that was 0, you see this right hand side. So using star 20, we see that the right hand side actually gives us 0. But now if we write OA as phi of x and OB as phi dagger of y, then we know that this LHS is not 0. Okay, so we get a contradiction, right? So that means this is not satisfied by our complex scalar field. Okay. So when you choose OA and OB like this, and using the vanishing of the 1 point function of the vacuum expectation of the phi, the right hand side goes to 0, but the left hand side is non-zero. So it means this is a contradiction. And what is this a contradiction to? The assumption that we started with. So what did in this whole game, what did we assume? We had assumed that the Hilbert space nicely factorized, the vacuum nicely factorized, but that factorization, that means, is not true in the complex scalar field case. So this factorization isn't true in the complex scalar field case. So this means that when you write down a generic vacuum, you cannot write it as like this between two space-like separated regions with A and B space-like separated. So this means that there exists. So this translates to saying that there exists non-local and non-vanishing correlations with a vacuum, and the vacuum is an highly entangled state. Okay. So here I am using a definition which I will not go into, but the definition of an entangled state. So the definition of an entangled state is one that cannot be written as a product state. Okay. If something cannot be written like this, then that will be defined as an entangled state. And that's what we see. And that's why this non-vanishing, so this is why this non-vanishing thing for space-like separations is often called that the vacuum is highly entangled, because you cannot write your theory as a product decomposition. Okay. Now let's see how the notion of causality fits into this. Let me look at the chat. There was a question. Okay, so there's a question about time ordering. We will do that very soon. Now but recall that this thing was 0, right? When we looked at the commutator, that was indeed 0, and we defined the notion of causality from this. Now you see, if we expand this side, what we get? We get phi x phi dagger y and minus phi dagger y phi x, just from the definition of the commutator. And also we had argued that this guy was just a number, and that you remember that this thing was just 0, right? So this was just 0. So that's why since that was just a plain simple number, you can put the commutator inside an operator like an expectation value, and when you do that, you get these things. Okay. So expanding out the commutator, you get a term like this minus a term like this. So this is just expanding the commutator. Okay. But now something interesting happens. You see that let's now put back the 0 properly. So you have phi dagger 0 minus 0 phi dagger phi. And now recall, what did phi dagger do? So phi dagger, let me also explicitly write x and y, and this was y and x, right? Yes. So what did phi dagger do? So phi dagger created when acts on the vacuum, we know that it created a particle at y, and phi x. So like here, it creates an antiparticle at x. So this part of the equation, you create a particle at y, and then you measure it at x. Okay. For the other part, you create an antiparticle at y, at x, sorry, and then you measure it at y. Okay. And they precisely cancel each other to give the commutator to be 0. Okay, that's what happens, and you get this 0. So the physical reasoning behind that was this. So this means even though you have non-vanishing correlations with the vacuum for something that's very far away in space-like regions, you cannot transmit any signal to that point. And the reason is, if you do that with a particle, and because of the charge conjugation symmetry, we also have an antiparticle that will go in the other direction, and it will precisely cancel off if you try to signal something. And hence, the net transmission would be 0. Okay. And you see this, that from Schrodinger equation, we could not have argued this, because Schrodinger equation was a quantum theory where particle number was conserved, and there was no production of particles and antiparticles whatsoever. But the importance of particle-antiparticle pair is, now we see it helps to define a notion of causality even when you have non-trivial correlations among space-like separated points. So such correlations are fine. That's what called entanglement, or here we did this over a vacuum state, so it's called vacuum entanglement. But if you do it on an arbitrary state, it's just entanglement. So those non-vanishing things are called entanglement, and that has got to do with, because you cannot factorize your theory into A and B sectors. But that doesn't break causality, because as soon as you try to send a transmission with the help of a particle, it will have an antiparticle that will cancel it. So causality will be preserved. And so this is why this notion of microcausality works even when we have non-zero correlation. And in the beginning, we motivated this and connected this also to independent and measurements which are not independent of each other, which is something that you already know from diagonalizability and non-diagonalizability in quantum mechanics. Like X and P are, since they don't commute, you cannot find a simultaneous eigenstate, but you can do that for Q and H, let's say. So that was the motivation behind the definition, and now we see in practice that causality indeed holds. Even after you have non-trivial correlations, you can't do this. Okay, let me actually explain this thing in a very like in a simpler way, that what does this entanglement does then at the end. So this entanglement is something like this. So imagine you have a left-handed glove and a right-handed glove. Okay, so I'm talking about gloves that you wear in winter. So then now what you do is you give one to your friend and another you take and run away somewhere, like let's say to the Andromeda galaxy or something, which is space like separated away from you at that very instant. So now if your friend opens the box and finds a left-handed glove, then somehow your friend knows that you will have a right-handed glove. Okay. And that's because these two states are entangled, but there is no information transfer between them. Okay. The knowledge comes from the fact that there were only two states to begin with. So once your friend's state collapsed to left, your state will be right, but there is no instantaneous signaling happening. So the physics of all this is that you have an entangled state, and the thing that forbids instantaneous signaling is there will be a particle that will be exactly cancelled by its antiparticle, and they will always come in pairs. Good. Isn't and isn't phi x create antiparticle? Uh, no. So I said that this creates a particle, this part, and this creates an antiparticle. So if you take the Hermitian conjugate, then that will be different now. If you are focusing on this part, they will exactly be the reverse of each other. Okay. But we define particle and antiparticle just by looking at the bra excitations, which is excitations acting on the vacuum, the the bra representation of the vacuum. An analogous one-to-one story is also there for the ket representation. Okay. So you can again argue for the ket, but all this we did for the bra part. Okay.
Just one question.
Sure.
My friend has the entangled state, and I have the entangled state. So if I measure my state, if I look at it, if I observe it, it's left-handed. So his state will also collapse to right-handed, or
Yes. His state will also collapse to right angle at that very moment. But this is not an instantaneous signaling thing. This is just because those states are entangled. That's why.
okay.
Yeah. So nobody. So what do I? Thanks for the question. What I mean to say was nobody communicated this between you and your friend. You just knew this that it happened the moment you opened it because the way we had constructed these states was that they were entangled. Okay.
So the other state will also collapse at the same moment.
Yes. If to begin with you had an entangled pair of gloves, then only.
Yeah.
Or as we said, like if you have a non-factorizable Hilbert space.
Yeah.
Thanks.
Thank
Okay.
you.
Yeah, thank you. Now, for the remaining 20 minutes or so, let's move on to the Feynman propagator. Okay. So this is where we will now introduce time ordering, which was a comment in the chat. Okay. So for that, let's understand what is time ordering. So a symbol time ordering will be denoted like this, O1x1, O2x2, and dot dot dot. And if this is the case, then I can write it as like this. If the time for x1, so that is t1, is greater than t2. So all it means is that in a chain of operators, if you time order them, the operator which comes later will be on the left, and the operator which comes earlier will be on the right. Okay, so this is what time ordering means. Now with that, we will be interested to compute a propagator g x prime, which we will compute, and the propagator will be this t, so time ordered of phi x prime and phi dagger x acting on the vacuum. So the vacuum expectation value of this quantity. Now let's unpack what this quantity looks like using the definition of time ordering. So this quantity is, I'll explain what these thetas are. So you can write them as this plus theta t minus t prime phi dagger x, phi dagger x phi x prime. So theta is a function which is, so theta of t is a function which you can graphically draw like this. So it's just 1. So theta of t and t. So it's just 1 when you have t greater than 0 and 0 if you have t less than 0. So this is why if the argument of phi, that is t prime, the time argument is greater than t, so then this is just 1. So that's why you have phi coming left. So it's the later field. Phi dagger comes early. But if you reverse that, you get phi dagger and phi. Okay. This is what is called the Heaviside step function. And there is an interesting identity again, which if you know, you know, and if you don't know, it will be there in the appendix, that the derivative of the theta function is actually what is the delta function. Okay. So this is an identity that you will be needing to perform many computations. And as I said, if you know this, you know, or I'll write this in an appendix. So that's the quantity. So this is the quantity when you expand out the time ordering product, and you can do that with this step function. Now let's compute this quantity G. Okay. So that's what we will do next. So if we do that, we get this thing. Okay. Theta t prime minus t. So using the theta functions, we can now explicitly write the G out 1 by 2 omega k and e to the power minus I omega k t prime minus t plus I k dot x prime minus x and plus theta t minus t prime d3k by 2 pi cube 1 by 2 omega k, and it's the opposite signs of what we wrote. T prime minus t minus I k dot x prime minus x. Okay. Again, I'm just recalling that these bars are vectors. Okay, so they are actually arrows. So you can write this, and so essentially, sorry. Oops, I stopped my iPad. Yeah. So essentially what we, sorry, I think the screen sharing stopped. Yeah. Can you see the screen again? Yeah. Can you see the screen again? It was paused for a moment.
Yes, we can see it.
Okay,
Thank
perfect.
you.
Yeah. Sorry about that. Yeah. So here again, you express these things. So essentially what I
No
did was
problem.
I expanded this out using the step functions, and I wrote them in ladder operators, which we have been doing this class when we are computing propagators, and that gives you this. Okay. Now, uh, we will do an interesting computation in complex analysis as to how to evaluate this. Okay. So, so for that, let us try to express this thing. Okay. So before that, let me mention to you that you see that when t prime minus t is greater than 0, that is this part, then the evolution happens with a factor like this. Okay, t prime minus t. But when t prime minus t is less than 0, which is this part, then the evolution happens with exactly the opposite time ordering. And that's what time ordering does. However, as we have discussed time and again, the space plus and minus are nothing more than a relabeling. Okay, because along space direction you can flip them. So that part is a relabeling, but the actual physics is captured in the time ordering. Okay, so you cannot relabel time because it's a unidirectional thing. Now let's write down a covariant form of this propagator, and then we will see how to use complex analysis. So a covariant form of this propagator can be written like this. Gx minus x prime is, so this I will play a crucial role when we evaluate this using contour integrals in the complex plane. That's why this I comes about. And you can write this as x prime minus x. So now this is 4 vector notation over k square minus m square. Okay. So we can write it like this. Now let us argue So let me call this star 21. So now let us argue that, and let's call this star 21 prime. So now we will argue that they both are equal. So star 21 prime is indeed equal to star 21. So this is where we will use contour integration. So we can write down this g above as an integral over space and okay, minus infinity to infinity, the time part, e to the power I k0. Now I am explicitly writing the time and the space part separately, times e to the power minus I k x minus x, sorry, x prime minus x. Okay. Okay, so one small thing. So at times I will be writing k0 and k0 without any difference. But you know that in our convention, which is plus minus minus minus, so they are essentially same. So I'll try to be consistent, but at times I will do up and down in the time index, but it's fine in this convention. Okay, now let's see how to evaluate this integral. Okay, so to evaluate this, I will define the time integral as this quantity. I just let me call it just I as this integral. Okay, so we will perform the time integral first. And we will, oh, sorry, there was a k square omega square, which I forgot. Let me bring this down. So I forgot a factor here. So then this, did I forget that factor anywhere else? No. Yeah. Let me just quickly check. Yeah, this is fine. So this, and then there's an overall factor of k square minus omega square, which you can write as k0 square minus omega k square. So this factor, okay? So I had forgotten to write that factor. This is this factor. So now let's evaluate the time integral. Okay, that's the time integral. And let's split it up like a plus b and a minus b, just like we did before in the beginning. Okay. Now you see there are poles. So this integral has poles. Poles are where this integral diverges at plus minus omega k. So we need to do something nice now to evaluate this. Okay, so because there are poles, so we need to be careful. So this is where complex analysis enters. So to begin with, this is my k0 space, and this is the imaginary part of k0. And the poles lie here in the real axis at minus omega k and plus omega k. Now I will describe a prescription, and then we will see that that prescription indeed gives us the right answer. So the prescription is this, that we go from here. So we start from minus infinity on the real axis because that's the integral domains. And then we go, actually, let me write this up and this, yeah, that's down is fine. So we go down this pole, and then we go all the way here, and then we go up this pole. Okay. So that's how I will specify my contour. So from minus infinity to plus infinity. So the negative pole I will go below, and the positive pole I'll go above, and we will see why we take this prescription. So for now, just take it from me that this is the prescription we'll be using. You can do the opposite thing, but that will give you something different. So that's why let's take this. And then what we will do is we will either close the contour. So we need to close the contour upwards, or we will close the contour downwards. Okay. And now let's do that. And again, as I said, I will put up an appendix on complex analysis and residue theorem calculation, but I will not derive them here. So using that, so now let's see how we close the contour. So let me call this contour 1 and contour 2. So what dictates how we close this contour? Okay. So for that, we have to zoom in on this factor, okay, e to the power ik0. So that's the factor that we will decide, where to close the contour. So let's look at this part. Now see that if you take k0, so if you look at this factor and if you take k0 all the way to I infinity, so that means you want to focus on this part of the contour, the one, and then you take this contour and take it very large. Then what you get is e to the power minus some number which is like infinity, because it goes to I infinity, so I square gives -1, and that goes to 0 when you increase the contour all the way. So you get a decay here. So that's why when we take the upper part of the contour, what we will do is, you see, now let's draw that contour again. So this was the contour, right? And we saw that if we take this part, then and the poles were here, okay. So that means when you now do the computation, you will encircle by doing this thing, this pole, okay, this pole. So when you do that, when you go in the upper half plane of the complex plane of k0, you encircle the negative pole. Now that is the case which makes sense when t prime minus t is positive, okay, because if t prime minus t is positive, then this thing will decay like the exponential decay. So for the case where t prime minus t is positive, that is when you have the term that multiplies theta t prime minus t, we will consider the upper half plane, and that will encircle sorry, the negative pole, which is this minus omega k pole. Now for the other case, when t prime minus t will be negative, that is the term that multiplies this thing. So that's the case when t prime minus t is negative. We will exactly do the opposite thing. Why? Because now you see, again, zoom in that factor, e to the power I k0 t prime minus t. Now because this is negative, this becomes I k0 t minus t prime, right? T minus t prime with a negative sign, okay? So overall it's negative. So now if you take k0 to minus I infinity, then you to the power minus infinity times t prime minus t, okay? So this is again just a simple argument that because this exponential flips the sign when t prime minus t is negative, so you have to take k0 in the negative axis. So when you do that, now this was our pole contour prescription, and these were our poles. So now you see, and this is the direction from minus infinity to plus infinity. So now we will encircle below, so in the lower half plane. So doing that picks up this pole. So essentially this boils down to saying you will evaluate about P. But there is a slight catch. The catch is this encircling that we did here. This was anti-clockwise, and hence the phase that we got here was plus. But this is clockwise, so the phase that you will get is minus. So if you put all that together and use what is called the residue theorem, again, this will be there in the appendix of complex analysis. So if you do the residue theorem, so in the upper half plane, the residue will peak from the negative pole minus omega k is just this quantity. So it's that function evaluated at I omega k, but excluding the pole part, and e to the power minus I k x prime minus x divided by minus 2 omega k. And this minus comes from the fact because we are evaluating the negative pole. So the residue gives this, and the integral I1, which is the upper half plane integral, is by the residue theorem 2 pi I times this residue, this quantity. Okay. So similarly, if you do for the lower half plane, you get 2 pi I times the residue 2. And this is the residue theorem, which I am not proving. So now if you do that, the only difference you will get, yes, and as I said, there will be a -1 here because of the different circling of the integration. And this should be obvious because when you go from minus infinity to infinity, just in one-dimensional integral, and you flip the domains, you pick up a minus sign. So in complex plane, that the analog of that is this. So if you complete the contour clockwise or anti-clockwise, you pick a sign. And hence, you will pick a sign in I2. And finally, when you write I as I1 plus I2, you get that this gxx prime becomes theta t prime minus t, an integral e to the power minus I omega k something times e to the power minus I k times something plus theta t minus t prime, again an integral e to the power plus I omega k and e to the power minus I k. And just as I said, we are relabeling, and there was a question as in why we always relabel the second term. Now we will relabel the first term. So relabel here k2 minus k, and that will turn this sign to positive. Okay. And this is indeed star 21 prime. Okay, the equation that we started with, this one, when was written in terms of this. So what we proved using complex analysis was this quantity 0 t phi x. Sorry, let me see what convention I used. Yes, phi x prime, phi dagger, phi x prime, phi dagger x. This is indeed this covariant integral. Okay, now written nicely in a covariant way. E to the power I k dot. Let me write it below. K dot x prime minus x over k square minus m square. So this is what we showed. So I'll take 10 more minutes and I'll complete this part. I hope that's fine. Okay.
Yeah, absolutely fine. Thank you.
Yeah. So I would avoid looking at some of the questions now because I'm running a bit out of time. You can post them on the Slack. Okay. So that's what we get. And yes, now you see that this prescription that we took here, this exact prescription indeed gave us the right propagator that we wanted to prove. And hence, we take this prescription. If we had defined our propagator differently, like that gave us this quantity. So this equality crucially depended on how we took the prescription. So if you would have defined this differently, then you could have worked with the other prescription. Okay. But the way I am defining things, that's the prescription that gives me this thing. And this is what is called the Feynman propagator. Okay. And as you have seen by now that, yeah, Now that this propagator could be expanded in terms of just this field, right? So we saw that using this, we could write this Feynman propagator with this time ordering as this normal propagators that were there, which had non-vanishing correlations. Okay, like if you take the time ordering with the commutators. Okay, so now let's talk about a bit about something that people call the I epsilon prescription. So so it is again this integral written in this covariant form, but we will slightly tweak it. So this is what people mean by the I epsilon prescription, and we will see why it's useful. So we had this integral. So this is exactly that, but now we add a term where epsilon is a very small parameter. Okay, and you see what it does is this. So let's expand out that thing. So minus omega k square plus I epsilon is 0. So these are the roots, or where you get the poles. So roots of denominator or poles. So that means k0 square is omega square minus I epsilon. And now if you look for very small epsilon, you can expand the square root. Sorry, and this will give you k0 plus minus omega k 1 minus I epsilon by 2 omega k. So this is just, bringing the half in the square root to down. So you see what happens to the positive pole. So the positive pole is plus omega k and minus some number I epsilon over 2 omega over 2, right? And the negative pole is minus omega k plus I epsilon over 2. And that's exactly what this upper half and lower half business did. So recall that in the upper half plane, we got the minus pole, and in the lower half plane, we got the plus pole. So this is exactly what this I epsilon prescription does for you. So it shifts the positive pole uh, lower. So it lands you in the lower half plane when you continue in the lower half plane, and it shifts the negative pole slightly upwards. So that's why we had seen that we were evaluating it in the upper half plane. So this I epsilon prescription, when you write the denominator as a small imaginary number, it essentially gives you this correct shifting of poles prescription that was needed to evaluate. Now, one last thing I will do and I'll stop. So you can now check that if you recall that for a real scalar field, we had the equation of motion as del square plus m square phi as 0. So if you compute this del square plus m square on this green function, this Feynman propagator, it's also called the Green's function. So if you compute it on this, it's very straightforward. One thing you have to do is when you act del x, then you get a minus k square, okay, in the 4 vector notation. So because this del will act here, the del square, and that will bring minus ik twice, so you'll get a minus ik square. So if you do that, what you get is this quantity, okay, d4k over 2 pi 4 e to the power ik dot x prime minus x And as you know, this is just uh, delta. And this is something that we said yesterday, that the identity, the Fourier transform of identity is just the delta function. So this means that the Feynman propagator satisfies the equation of motion with a delta function source. Okay, so this is the source. So if that's 0, then you say that you don't have a source. And why this is necessary? Because now you see that we argued something that was called on-shell quantities when we said that the equation of motions were satisfied. Okay, so the equation of motion satisfied, meaning that recall that we had expanded in the momentum space our modes, and we had gotten something like this, right? So on momentum space, this is what the Klein-Gordon equation or the equation of motion looked like. So, and all of these guys, they satisfied this relation, right? K square equals m square. And then only you have a non-trivial solution for this equation. Let me call it star tilde. So these are what are called real particles. So particles which you observe and they satisfy equation of motion. And that's why particles which satisfies this condition are called on-shell uh, condition satisfying particles, okay? Or real particles. Now note that but if you solve the propagator, if you add the propagator on the Klein-Gordon operator, you get a source and you don't get that it's 0. So if that's the case, then the propagator will involve particles which don't satisfy the equation of motion, or in other words, they break this condition, okay? And this is also called the mass shell condition. So they break this condition. So anything that the propagator describes, which is like transitioning of your interaction or anything, because that's what signals your, as we argued, that's what signaling of uh, a transmission would be. So it turns out that will be that will involve particles that don't satisfy the equation of motion, or what are called virtual particles. Okay, and I won't say more about this in the next section, next set of lectures, which will be given by a different lecturer. When you will study interacting QFT, you will see that you will draw Feynman diagrams where there will be particles, physical particles in your lab that you observe. So these are like at your asymptotics. So these are particles which satisfy equation of motion and they are on shell, and that's why they are on shell. But there will be particles in between that carry some interactions which will be called virtual particles. And those are virtual because they don't satisfy the equation of motion, and they are that's why they essentially capture what the propagator does. So it carries the propagation of some interaction or whatever you are studying, like a scattering of particles and things like that. So that is what is captured by the propagator, okay? And we explicitly showed that it doesn't satisfy the Klein-Gordon equation exactly. It satisfies the inhomogeneous Klein-Gordon equation with a delta function source. Okay, so I think that's the content that I wanted to talk about today. And with that, we come to the end of the lecture. Sorry for going 3-4 minutes over time, but if you have any doubts, I can answer them in the next couple of minutes. And the remaining doubts you can post on Slack.